Hello students, in this question it is given that there is a solenoid of length L having radius R, where radius is very small as compared to its length, so we will assume it's a long solenoid. A steady current flows through the solenoid, and it is also given that magnetic field is uniform inside and zero outside. So that is given. And we have assumed that this solenoidal length is along this direction that is given. This is Z and it is connected with some battery. So current will be flowing in the phi cap direction. This is the direction of current. Now among the given option, choose the one that best represents the variation of magnitude of vector potential, and that is A phi component at a distance Z is equal to L by 2. As a function of radial distance. We have to see as a function of radial distance R in cylindrical coordinate. And this del cross F formula is given in cylindrical coordinate. So 4 options are given. You can see we have to verify which one is the correct. So A phi versus R we have to verify. So let us consider a long solenoid. Let's assume we have a long solenoid. It's a very long solenoid, having radius small r, capital R, and also assume current is in the phi cap direction. Let us assume this current is in the phi cap direction. We have some current and assume this as the Z direction. So we know that for R less than R, this magnetic field B is some constant, and if you see the direction, that will be in the Z cap direction, and if you see outside, magnetic field B is 0. That we know, and that is given also. We have to find vector potential. So let's consider this is the axis of the solenoid. So in this case, current is in the phi cap direction. The current is in the phi cap direction. So vector potential A is also in the phi cap direction. So it has A phi cap component. Now in this case we will use integral form of this equation. This is closed A dot dl, that will be given by, this is the closed line integral, is equal to surface integral B dot d. We will use the integral form. So for inside point, we have to see at Z is equal to L by 2. This is, let's say this is at L by 2 distance, and at this point draw a loop of radius small r. So this is the direction of n cap, and magnetic field B we know that is uniform. This is B, some constant value, outside B is 0. So if we write close A dot dl at point P, that is inside. So for inside point, we can write this as mod A into 2 pi r. A and dl both are in the phi cap direction. And this surface integral B dot dA is given by B and dA, they are in the same direction. So we will write B as some constant value, and dA is given by pi small r square. So if we see the dependence of the magnitude A, and that is simply A phi component, this will be proportional to R. So inside it is proportional to R. Now for outside point, we will use same equation. So at same distance, if we draw this loop of radius R, now field is varying in this region only. So for outside point, we can write mod A into 2 pi r, and that will be given by inside magnetic field is constant and this field is varying from 0 to r only, capital R only. So we will write it here pi capital R square. So this will give you mod A is, that is again A phi component. This is inversely proportional to R. So inside it is proportional to R, outside it is inversely proportional to R. So if you verify this option, you can see in option C, this is proportional to R and outside it is inversely proportional to R. So option C is correct. Hello students, in this question, it is given that consider a tiny current loop driven by sinusoidal alternating current. If the surface integral of its time average Poynting vector is constant, then the magnitude of the time averaged magnetic field intensity at any arbitrary position r is proportional to, four options are given, 1 by r cube, 1 by r square, 1 by r, or proportional to r. So in this question it is given that closed time average Poynting vector s dot dA is a constant value. Now it's a case of a small current loop. So it's a case of a, you can say, oscillating magnetic dipole. It's an oscillating magnetic dipole. We know that Poynting vector S is given by E cross H, where H is the magnetic field intensity and E and H are related. So its time average S is, we have to find time average of E cross H. Now we know that this dA is proportional to R square. So S dot dA, if it should be a constant, it means this time average S should be proportional to 1 by R square. So this should be proportional to 1 by R square. This implies that time average of magnitude of E is proportional to 1 by R, as well as time average of magnitude of magnetic field intensity H is also proportional to 1 by R. So option C is correct. Hello students, in this question it is given that there are two concentric conducting spherical shell. So it's a conducting spherical shell as shown in this figure. The inner shell that has radius A carries charge plus Q. So this carries charge plus Q. And the outer shell radius B carries a charge minus Q. So outer shell carries charge minus Q. The empty space between them, half is filled by hemispherical shell of a dielectric having permittivity of epsilon 1. So this is the dielectric and its permittivity is epsilon 1. The remaining space between the shell is filled with air having permittivity epsilon. So this is filled with air and having permittivity epsilon. So in this question we have to find the electric field at a radial distance r from the center between the shells, that is R lies between A and B, what will be the electric field? So these four options are given and we have to verify the correct one. Now see, in this case, these are the conductors. So charge plus Q will distribute uniformly over the inner shell. This charge will be distributed uniformly. And due to this, let's say if this is positive charge, this dielectric will get polarized and bound charge will develop. In free space, there is no polarization. In free space, there is no polarization. So we don't know the bound charge and we have to find the electric field, let's say at any point P that is small r distance away. So we will use the Gauss law, and in Gauss law, let's draw a Gaussian sphere of radius small r. This is the Gaussian surface, and this Gaussian surface is a sphere. Now we cannot use charge enclosed as epsilon naught E dot dA because we don't know the total charge. So we will use this equation in terms of D vector. So that is given by D dot dA, and this must be equal to only free charge enclosed. We don't require bound charge, we require only free charge. And how to define D in air and dielectric? So let's say in air, we will write it as D naught. This is, we are writing this vector in air. And this D naught vector is given by epsilon naught E, where E is the electric field at r distance away. And in dielectric, we will write this equation D1 as epsilon 1 E. So we will use these equations. So if we write closed D dot dA in spherical symmetry, we know that can be written as mod D into area of the sphere, but here you have two separate regions and their area will be half. Half area is for air and half area is for dielectric. So if we expand this, that can be written as D naught into radius is small r. So area of the Gaussian sphere is total area is 4 pi r square. In air it is half. Plus in dielectric again D1 into 4 pi r square divided by 2. And what is the total free charge enclosed? That is simply Q. Now we can rewrite this equation as D naught is epsilon naught E into 2 pi r square, and D1 is epsilon 1 E into 2 pi r square, and that is equal to Q. Now we can write this as E naught. This is E epsilon naught plus epsilon 1 2 pi r square. You can take common, that is Q. So E can be written as Q by 2 pi epsilon 0 plus epsilon 1 r square. And if we see the direction in spherical symmetry, electric field has radial direction, so that is r cap direction. Now we see the different options. If you see option 1, that is Q by 2 pi epsilon naught plus epsilon 1 r cap by r square everywhere. So this option is correct. Hello students, in this question it is given that an electromagnetic wave having electric field E is 8 cos kz omega t y cap in units of volt per centimeter is incident at 90 degrees. So it's a normal incidence on a square slab from vacuum with refractive index 1.0. So it's an air, refractive index is 1. As shown in this figure, the slab is composed of two different material with refractive indices N1 and N2. So you know N1 and N2. Assume that the permeability of each medium is same. After passing through the slab for the first time, what will be the electric field amplitude in volt per centimeter of the EM wave which emerges from slab in region 2? So that will emerge in region 2. 4 options are given. We have to verify the correct one. So let us first see at the interface of slab what will be critical angle. So let us assume this is the normal and let's say this is the critical angle, and at critical angle this reflected light is just parallel to the interface. So we know that if you apply Snell's law at the interface, so sin theta c, this angle is 90 degree. So sin theta c by sin 90, that will be given by n2 by n1. So theta c is sin inverse 1.1 by 2.2, and that value is what? Half. So theta c is sin inverse 1 by 2. So this will be 30 degree. So critical angle is 30 degree. That we know. Now see, it is given that this is the air. So N0 is 1. This is also N0 is 1. So you have a normal incidence. So at this point, this angle is also 45 degree. So if we take normal, so this angle is also 45 degree. It means this is theta I. So this theta I is 45 degree, and that is greater than the critical angle. Critical angle is 30 degree. It means there will be total internal reflection at this interface. So if this intensity is I naught, assume this intensity will be, let's assume this intensity is I1. I am taking this intensity as I1, and then again this intensity is I2, and this intensity is I3. So you can see because of total internal reflection, intensity I2 will be equal to I1. And this I naught intensity, that is given by half C epsilon naught E naught square, where E naught is 8 volt per centimeter. So as you can see, this E is given, where this 8 is the E naught in volt per centimeter. Now we have to see what will happen at interface 1. So at interface 1, there is a normal incidence. So we can write transmitted coefficient T1, and that will be given by 4 N1 N0 by n1 plus n0 whole square. And if we substitute this value, this is 4, then you have 2.2 into 1 by 2.2 plus 1 whole square. And if we solve this value, you will get 8.8 divided by 3.2 into 3.2. And that value will be 55 by 64. We can easily rearrange in this form. Then I1 will be given by T times T1 times I0. And this T1 times I0 will be 55 by 64 I0, and that must be equal to I2, because we know that due to total internal reflection, IT is equal to I. So we will take interface 2. Now at interface 2, again we have a normal incidence. So this T2 is given by, again you have to use same relation for N1 N0 by N1 plus N0 whole square. N1 N0 is same value, so if you calculate this, you will get same 55 by 64. Now we can write transmitted intensity I3 is given by T2 times I2, and this T2 is 55 by 64. I2 we have calculated this value, that is again 55 by 64 into I0. Now we will write I3 as half C epsilon naught. Let's say amplitude will be E03 square, and that will be 55 by 64 whole square into I0 is, that value will be given by half C epsilon naught E0 square. So this half C epsilon naught will cancel out, and this will give you E03 is 55 by 64 into E0. E0 we know 8 volt per centimeter, so this is 55 by 64 into 8 volt per centimeter. And if we calculate this value, this will be 55 by 8, and that we can rearrange as 11 by 1.6 volt per centimeter. Now if we see the option A is 11 by 1.6 in units of volt per centimeter. So option A is correct. In this question, it is given that a material is placed in a magnetic field intensity H. As a result, bound current density JB is induced and the magnetization of the material is M. The magnetic flux density is B. We have to choose the correct options valid at the surface of the material. So we know that when a magnetic material is placed in an external magnetic field, it gets magnetized and bound current will develop. So volume bound current density is given by del cross M. This is JB, and KB is given by M cross N cap. We know these relationships. And we also know that B is given by mu naught H plus M. Now since divergence of B is 0, this is always 0. So this will give you 0 mu naught divergence H plus divergence of M. And this will give you divergence H is equal to minus of divergence of, and that is non-zero. So this is non-zero. Divergence of B is 0. Now it is given that this JB is del cross M. So let's calculate divergence of JB. So divergence of JB is divergence of a curl of M. And divergence of a curl is always 0. So it means divergence of JB is 0. So if we verify these options, you can see option A is incorrect, divergence M 0, but it is non-zero. Option B is correct because divergence B is 0. Divergence H 0 is incorrect because that is non-zero, and divergence JB is 0. So option B and D are correct. It's a multiple select question. So let's see next question, that is, as shown in figure, electromagnetic wave with intensity II is incident at the interface of two media having refractive indices N1 is 1 and 2 is root 3. So it is given that N1 is 1 and N2 is root 3. The wave is reflected with intensity IR and the transmitted with intensity IT. Permeability of each medium is same and the reflection coefficient R is IR by II and the transmission coefficient T is IT by II. Now four options are given and we have to choose the correct statements. So first option is R is equal to 0 if theta is 0 and polarization is parallel to the plane of incidence. B is T is 1, theta is 60 degree and polarization is again parallel to the plane of incidence. C option, R is 0, theta is 60 degree, polarization perpendicular to the plane of incidence. And D option, T is 1, if theta is 60 degree, again polarization is perpendicular to the plane of incidence. So let us first calculate what will be Brewster angle at this interface. So that Brewster angle theta B. So let's take theta I, that is equal to theta B, and this particular angle is given by tan inverse N2 by N1, and that is simply tan inverse under root 3 by 1. So theta I is equal to theta B is 60 degree. So Brewster angle is 60 degree. Now what will happen at this particular angle? So we have already calculated that theta B is 60 degree. Now we have to note 2 points. Point number 1 is, if the incident light if the incident light is in the plane of incidence, POI means plane of incidence, then at theta B, R will be 0 and T will be 1. So reflection coefficient will be 0 if light is in the plane of incidence. Now second point, again we can see if the incident light is perpendicular to the plane of incidence, then at theta B, R is non-zero, then T will be also not equal to 1. So if we see for option, as we have already seen that theta is equal to theta B is 60 degree. So we have to see these three options. Now R will be 0 and T will be 1 only if incident light is parallel to the plane of incidence. So in that case, you can see option B, T is 1 when theta is 60 degree, that is this case, and in neither option R is not equal to 0 and T is not equal to 1. So only option B is correct. Although it's a multiple select question, but in this case only option B is correct. Hello students, in this question it is given that consider a cross section of an electromagnet having an air gap of 5 cm as shown in this figure. It consists of magnetic material having mu is 20,000 mu naught and is driven by a coil having Ni is 10 to power 4 ampere, where N is the number of turns and I is the current in amperes. Now ignoring the fringe field, we have to find the magnitude of the magnetic field B in the air gap between the magnetic dipoles, and we have to write it in Tesla, and you have to round it off to 2 decimal places. So in this question we will use Ampere's law, that is close H dot dl is free current enclosed. So if we consider a closed path, let's consider a closed path that includes the core region as well as the air gap region. So this is the air gap region. And if we write this equation, let us see field in core region represented by Hc, and in gap region if we represent it by Hg, and let's take Lc and Lg, they are the core and gap length, core and gap length. So we can write this equation as Hc into Lc plus Hg into Lg, and that will be free current enclosed will be N into I, and we can write H as B by mu. So Hc can be written as Bc divided by mu c, and mu c is 2 into 10 to power 4 mu naught, and this is Lc plus this will be Bg by mu g is mu naught Lg, and that is Ni, Now if we compare these two, this term can be neglected as compared to the gap term. So we can write Bg into Lg by mu naught is approximately Ni, and that will give you value of Bg is Ni is 10 to power 4 into mu naught by Lg. Now Bg is 10 to power 4 amperes. Mu naught in amperes unit 4 pi 10 to power minus 7, and Lg is 5 centimeter or 5 into 10 to power minus 2 meters. So that you will get in Tesla. This much Tesla. So if we calculate this value, Bg can be calculated as, so we can write 4 pi into 10 to power minus 1 Tesla divided by 5. So this value will be 0.4 into 3.14 divided by 5, and this value will be 0.25 Tesla. So we have to write up to 2 decimal place. So answer will be 0.25 Tesla, and it's a numerical answer type question. So we have to fill here 0.25.